A-level maths, Surds. Before you start, you should know how to evaluate expressions involving powers, evaluate expressions involving roots, be able to work with negative, fractional and zero indices, be able to expand two brackets, and understand how to work out the difference of two squares. Surds are essentially square roots. Unless you're square rooting a square number, this will result in an irrational number. In other words, it can't be expressed exactly as a fraction where the numerator and denominator are whole numbers. Here's some examples of surds. Square root of 2, 3 root 5, which means 3 times the square root of 5, and negative 2 root 5. There are many other examples. In example 1, we'll look at how you simplify a surd. So in part A, we have the square root of 45. Now, the way to do this is to look for a factor of 45, which is a square number. In this case, we can use 9. So we can write the square root of 45 as the square root of 9 multiplied by 5. And that can be written as the square root of 9 multiplied by the square root of 5. And since the square root of 9 is 3, we have 3 multiplied by the square root of 5, which we write 3 root 5. Similarly, with the square root of 120, we're looking for a square number which is a factor of 120. Again, we can use 4. So the square root of 120 can be written as the square root of 4 times 30. And since the square root of 4 is 2, that simplifies to 2 root 30. In these examples, we have some expressions involving the addition of surds, and we're going to simplify these. So in part A, using the same method that we used in example 1, we can simplify the square root of 52 and the square root of 325 individually. Now 52 is 4 times 13 and 325 is 25 times 13, and so those surds simplify to 2 root 13 and 5 root 13. And now we have 2 root 13 add 5 root 13, so that gives us a total of 7 root 13. If we look at part B, again, using the same method, the square root of 8 can be simplified because 8 is 4 times 2. So we've actually got 2 root 2 plus root 2. So we've got a total of 3 root 2. And if we look at example 3, we have 6 root 72 added to root 8. Now first we'll simplify the square root of 72 and the square root of 8. Now 72 is equal to 36 times 2, and 8 is equal to 4 times 2, and so we can simplify the square root of 72 into 6 root 2, and the square root of 8 is 2 root 2. So we have 6 multiplied by 6 root 2, add 2 multiplied by root 2. Now the 6 multiplied by 6 root 2 is equal to 36 root 2, and when we add that to 2 root 2, we have a total of 38 root 2. Here's an activity for you to try. Here we have 11 statements, and what you need to do is decide whether each statement is true or false. So if you pause the video at this point, you can then write down your thoughts. If possible, try to justify your answers, and then when you're ready, play the video and listen to the explanation. So if we start with statement A, This is false. You cannot add surds in this way. And you can see in this case that the square root of 9 is 3, the square root of 4 is 2. So the left-hand side of that statement is equal to 5, and that's clearly not equal to the square root of 13. If we move on to statement B, the square root of 3 multiplied by the square root of 3 is the same as the square root of 3 times 3. In other words, the square root of 9, and that is equal to 3. That statement is true. And the same goes for statement C. The square root of 9 multiplied by the square root of 4 is the same as the square root of 9 times 4, which is the square root of 36. Moving on to statement D. The square root of 2 multiplied by the square root of 2 multiplied by the square root of 2 is the same as the square root of 2 times 2 times 2. In other words, the square root of 8. And the square root of 8 simplifies to 2 root 2, so that statement is also true. Moving on to statement E. 4 root 3 add 5 root 3 simplifies to 9 root 3, so that statement is true. And the statement at the bottom, statement F, 2 root 3 multiplied by 4 root 3 simplifies to 8 multiplied by the square root of 3 times 3. In other words, it's 8 times the square root of 9, not 8 times the square root of 3. So that one is false. Moving to the statements on the right hand side, if you evaluate the square root of 2 on your calculator, you get a value very similar to the value shown there. However, the square root of 2 is an irrational number, and the decimal number that is displayed on your calculator has been rounded off in order for it to fit on your calculator display. And for that reason, G, H and I are all false because the square root of 2 is not exactly equal to those decimals. Those decimals have been rounded off. Moving on to statement J, the square root of 9 subtract the square root of 4. If we work that out, that's the same as 3 subtract 2, which is 1, and that's clearly not equal to the square root of 5. And so we cannot subtract surds in this way. That statement is false. And the final statement, statement K, the square root of 36 divided by the square root of 4 is the same as having the square root of 36 divided by 4. In other words, the square root of 9. So that statement is true. You'll often come across situations where you need to multiply expressions together involving surds. So these examples look at how to do that. In part A, we're going to multiply 4 subtract root 3 by 7 add root 3. And we'll just do that by multiplying brackets together in the usual way. So here 4 times 7 is 28. 4 multiplied by root 3 gives us 4 root 3. Negative root 3 multiplied by 7, so we get take away 7 root 3, and negative root 3 add root 3 is negative root 9. So we can now look at that and simplify. We notice that 4 root 3 subtract 7 root 3 is negative 3 root 3, and since root 9 is equal to 3, we have 28 subtract 3, which is 25. And so the expression simplifies to 25 take away 3 root 3. Move on to part B and deal with that in exactly the same way. So first we multiply the brackets in the usual way. So these two terms multiply to give us 9 root 10. These two terms multiply to give us 12 root 4, which will simplify shortly. These two multiply to give us negative 6 root 25, and these two terms multiply to give us positive 8 root 10. and then we can simplify this. We have 9 root 10 and 8 root 10 here, so that's 17 root 10. Since the square root of 4 is 2, 12 root 4 is 24, and since the square root of 25 is 5, 6 root 25 is 30, so we end up with 17 root 10, take away 24, take away 30, which simplifies to negative 54 plus 17 root 10. Notice there that in part A and part B, the usual way of writing the answer is to write down the non-surd part of the expression first, and then the surd part of the expression second. If we move on to the other part of this example, we're going to do 7 add 3 root 5 squared, and that's the same as saying 7 add 3 root 5 multiplied by itself. So again, we have two brackets to expand and simplify, and doing that in the usual way is going to give us 49 add 21 root 5 add 21 root 5 add 9 root 25, or 9 times 5, which is 45, and then simplifying gives us 94, since 49 plus 45 is 94, and 21 root 5 and 21 root 5 gives us 42 root 5. Here's another quick activity, and this is designed to test whether you understand what you can and can't do when you're simplifying expressions involving surds. So what we want you to do here is look at the 8 pairs of expressions that you are given here, and decide whether or not the expression on the left-hand side of each pair is equal or not equal to the expression on the right. So spend a few moments trying this, pause the video, and then when you're ready, you can press play and listen to the explanation. So if we start with the first pair of expressions, those two are not equal to each other. And the best way to justify when they're not equal to each other is to find an example of values for A and B for which they don't work. Now we've seen in a previous example that if we use A equals 9 and B equals 4, we end up with the square root of 9 plus the square root of 4, which is equal to 3 plus 2, so 5, but the square root of 9 plus 4 is the square root of 13, and that's not the same as 5. And so we can use an example there to justify why that isn't correct. Similarly, you can use an example to show that B is also not correct. C, however, is correct, and when we're multiplying two surds together, we can simplify them in that way. So we have the square root of A multiplied by the square root of B, and that is always equal to the square root of A times B. And the same goes for division. If we have the square root of A divided by the square root of B, then that is equal to the square root of A over B. Moving to the pairs of expressions on the right, for the top one, those are equal, and that's since the square root of x squared is x and the square root of y squared is y, and so we have x plus y. However, it's not correct to say that the square root of x squared plus y squared is equal to x plus y. And again, you can find an example of values for x and y for which that doesn't work. If we move on to part G, the square root of x squared is x and the square root of y squared is y. So we have there x multiplied by y, so those two are equal to each other. And in a similar fashion, for the final pair of expressions, the square root of x squared over y squared can be simplified to the square root of x squared over the square root of y squared, which is x over y. So those are equal as well. We will often encounter fractional expressions that involve surds. And convention in mathematics is that we write these expressions in such a way that the denominator does not involve a surd. And the technique we use for ensuring that we write these expressions in the required way is called rationalizing the denominator. Now, these two examples are relatively simple examples, and the technique we would use here would be to multiply the numerator and the denominator by, in the first case, root 3. So since we are multiplying by root 3 over root 3, root 3 over root 3 is equal to 1. So we're not actually changing the value of the expression, we're just going to change how it looks, but it will still be equal to 1 over root 3. Now if we do this, the numerator becomes 1 times root 3, which is root 3, and the denominator becomes root 3 times root 3, which is root 9. And root 9 can be simplified to 3, which is not a surd. And so we've achieved our aim, which is to ensure that the expression is written in such a way that the denominator does not involve a surd. We have rationalised the denominator. For part B, we're going to achieve the same thing by multiplying the numerator and the denominator by the square root of 11. And that will mean that the numerator is the square root of 7 times the square root of 11, in other words the square root of 77, and the denominator becomes 3 multiplied by the square root of 11 multiplied by the square root of 11. And since the square root of 11 multiplied by the square root of 11 is the square root of 121, which is 11, the denominator becomes 3 times 11, which is 33. And so again, we've achieved our aim and written the original expression involving surds as a fraction where the denominator does not involve a surd, so we have rationalised the denominator. So these examples are slightly more complicated, and what we have here is that the denominator has two terms. We call that a binomial denominator, and in order to achieve our aim of rationalising the denominator, we need to of course multiply the fraction by something that's equal to 1 to ensure that it's the same value when we've finished manipulating it. And it turns out that the way to do this is to multiply the numerator and the denominator by what we call the conjugate of the denominator. And that simply means changing the sign which is associated with the surd part of the denominator. So in part A, where we have 7 subtract root 3 as the denominator, we're going to multiply the numerator and the denominator by 7 add root 3. Now since we are multiplying by something that's equivalent to 1, it's not going to change the value of the fraction, but it will change how it looks. Now what I like to do here is add brackets to the parts of the fraction there, and that makes it easier to see how to expand the different parts. So for the numerator, we're going to multiply 1 by 7 add root 3, and for the denominator, we're going to multiply those two brackets, 7 subtract root 3 and 7 add root 3, and we can use the same method that we used in previous examples to do that. And so we end up with the numerator being 7 add root 3, and when we expand and simplify the denominator, we end up with 49 take away 3, which equals 46. So we get 7 add root 3 over 46, and we have rationalised the denominator. We use the same technique for part B. So we're going to multiply the numerator and the denominator by the conjugate of 5 add root 3, which is 5 subtract root 3. And again, I would add brackets here to make it easier to see what to do. So we're going to expand and simplify the numerator by multiplying 1 add root 2 by 5 subtract root 3, and we're going to expand and simplify the denominator by multiplying 5 add root 3 multiplied by 5 subtract root 3, and when we do that we end up with 5 take away root 3 add 5 root 2 take away the square root of 2 times 3, which is the square root of 6, and then the denominator ends up being 25 take away 3. The numerator in this case will not simplify any further because we've got no terms which we can collect together, but the denominator will simplify, and so we get 5 take away root 3 add 5 root 2 take away root 6 all over 22, and we again have rationalised the denominator so that the denominator does not contain any surd terms.